This is an optimization problem from a past year term test. Pause the video to read the question. We're going to find the largest volume V that can be constructed by cutting the paper shape appropriately. There are various ways to solve this problem depending on the variable you use. We shall stick to the variable S. If we look at the final pyramid, the volume V is given by V equals 1/3 times base area times height, where the base is a square with side S, so the area is S squared. Let the height be H. The height is a perpendicular distance from the top of the pyramid to the base. EFC is a right angle triangle, so we can find H if we can somehow extract the length of FC and EC. To find these lengths, we consider the planar view of the paper before it is folded. First, let's put in some values. The dimensions of the inner square is S by S. The dimensions of the outer square is 20 by 20. F is in the center of the inner square, and FC is the hypotenuse of the right angled triangle with the other two sides as half S. Therefore, we can find FC because FC squared is equal to half S bracket squared plus half S bracket squared. Solving, FC is 1 over square root of 2S. Next, we find EC. Let's consider this triangle. This length is 10 since it's half of 20. This length is 10 minus FC, which is 1 over square root 2S. Therefore, EC squared is equal to 10 squared plus 10 minus 1 over square root 2S squared by Pythagoras theorem. Recall that H is part of the right angled triangle EFC. Therefore, H squared plus FC squared is EC squared. Therefore, H squared is equal to, so that H equals square root of 200 minus 10 square root 2S. The expression of V in terms of S is, with this expression of V, you can proceed to find the maximum V for the given S value. Firstly, we find the critical point by differentiating V. dV ds can be found by product rule, which is the critical point happens when the first derivative is 0. We have S is 0, which is rejected, or S is 8 square root 2. In summary, we have this. At this point, we can either use the second derivative test by taking the second derivative of V using quotient rule and check the sign when S equals 8 square root 2. Alternatively, an easier method is to use the first derivative test. To do this, we draw a table and consider the first derivative when S is 8 square root 2 greater than 8 square root 2 but less than 10 square root 2 and less than 8 square root 2 but greater than 0. Observe this first derivative expression. When s is between 0 and 8 square root 2, it is positive. When s is equal to 8 square root 2, it is 0. And when it is between 8 square root 2 and 10 square root 2, it is negative. Therefore, the tangent line on the left of 8 square root 2 goes up, and the tangent line on the right of 8 square root 2 goes down. So by the first derivative test, maximum v is reached at s equals 8 square root 2. The question requires us to find the largest volume. Therefore, we substitute the s value in the original v expression to get maximum v to be approximately 269.848 cm cubed.